In this tutorial, I will export an s11 graph and then I will go to an s21 graph and find the transmission zeros and insertion losses. Then finally, I will import s11 plot on s21 plot. Then I will discuss insertion losses and comparison between them. Let's go for it. This is s11 plot. You must go in post processor format file .txt file. Save it as a QS11. You can check here QS11. This is our exported result. Now I am going to check S21 parameter. Before going to S21 parameter, let me tell you few things. You can mark these frequencies as I already marked. If you don't know how to mark and how to find a bandwidth, you can go to my tutorial series. Mark these values and you can make a table of this frequency and how to find the bandwidth, like by here I am telling you. In this way, you can mark lower cutoff frequency and higher cutoff frequency of first, second, third, fourth band. You can make the table like this and you can find lower and higher cutoff frequencies. Now I am going to look at S21 plot. This is S21 plot. What is transmission zero? What are transmission zeros? If you don't know what are transmission zeros, where transmission zeros are created, why we check transmission zeros of S21 plot, and why transmission zeros are important. If less transmission of zeros comes out in a graph, what is the problem, and how we can create on transmission zeros at desired position. If you don't know the answer of these questions, you can search in my tutorial series. Basically, in transmission zeros, two transmission zeros created to create one pass band. In the start of pass band, one transmission zero is created. At the end of pass band, transmission zeros are created. Now I am going to mark the values of transmission zeros. This is first transmission, this is second transmission, this is third transmission, fourth transmission zero, this is fifth transmission zero, this is sixth transmission zero, seventh transmission zero, eighth transmission zero, ninth transmission zero. Basically, this transmission zero is not included. These we have an 8 transmission zero. Transmission zeros of first pass band are perfectly okay. That is why first pass band is made accurate, and similarly second pass band. But third pass band is not sharp and not okay. That is why third pass band is not accurate made. And similarly fourth pass band transmission zeros are very disturbed. We can make them correct, and to know how to make correction of these transmission zero, You can also check my tutorial and tutorial series, HFSS tutorial series. Similarly, how to find the insertion losses and what is insertion losses you can check also in my tutorial series. What are return losses you can also check it in my HFSS tutorial series. I am going to mark insertion losses of this graph. These are the insertion, and M10 shows the insertion losses of first pass band, insertion losses of second pass band, insertion losses of third pass band, insertion losses of fourth pass band. Now I am going to import the s11 graph to demonstrate how the insertion losses and how the transmission zeros are necessary in accurate positions. Click on right click and press import and change the file format from postprocessor.txt. Here we have already saved QS11, which I have saved S11 plot result. Click on open. Now holding down control key, press both the graph and move this graph down. These are the two graphs. Since S21 plot, how are you going to change the name? This is we have an S21 plot. What does S21 means? You need to know it. It means the power is given to port 1 and taken out from port 2. During this, insertion losses take place. Insertion losses take place in the result of insertion of load in a passband. Here you can see that this is the S11 plot. This is a passband. This is a first passband. Here the insertion losses take place, which are represented in M1, M10 in the result of insertion of load in first passband. Similarly, this is second passband. Insertion losses take place in the result of insertion of load in second passband. Here you can see that M11 shows that. Similarly, third passband. Here you can see that M12 shows the insertion losses of third passband. And similarly, this is the insertion losses of M4 passband. You can see that in first passband insertion losses are very small, almost near to 0 dB. It means it is a good passband. In second, there are little more insertion losses as compared to first passband. In third passband, there are too much insertion losses. That is why this passband is not created too much good. It must be necessary from the this peak must be lower than -10 dB needed. Similarly, fourth passband, there are too much insertion losses. That is why fourth passband is not created accurately. In this way, you can find the insertion loss. These M10, M11, M12, and M14 shows the insertion losses of quad band bandpass filter. As you know, the quad means four band. It is pass band filter. We have created a 4-band pass band filter. Similarly, you can see that two transmission zeros are created to create one passband. Here is accurate, here is also accurate. Here is some problem, and here is a very big problem. You can create one transmission zeros, and you can also adjust these transmission zeros. There, in this region, you have seen that the graph is not accurate. The problem is that the base matching does not occur here. That is why the graph is very disturbing. This way you can mark insertion losses in this way to transmission zero and make them in list and in table. Likewise, you can do for quad band. This is made it for tri-band bandpass filter. And what is fractional bandwidth? What is center frequency? If you don't know, you can search it in my HFSS tutorial series. Now I am going to mark the fractional bandwidth. It must be marked at -3 dB. You can check it is almost at -3 dB. Here you can see that fractional bandwidth we always mark it -3 dB because the S11 and S21 graph always touches at -3 dB because we are discussing practical bandpass filter, and practical bandpass filter does not possible to create to a passband or stop band at an exact and ideal position. Because of reality, we always take it -3 dB. Here I have marked for first passband. This is a low cutoff frequency at -3 dB, and 15 show, M16 show a higher cutoff frequency of first passband, M17 show the lower cutoff frequency, and M18 shows higher cutoff frequency of second passband, M19 show the lower cutoff frequency of third passband, and M13 show the higher cutoff frequency of M3. And similarly, you can see that M14 and M20 is a lower and higher cutoff frequency of fourth passband. In this way, you can mark the frequencies in a S21 plot at -3 dB for first passband, for second passband, and for third passband, and you can tabulate them in a table. And this is the fractional bandwidth formula: higher cutoff frequency minus lower cutoff frequency divided by center frequency. You can find center frequency by adding lower cutoff frequency with higher cutoff frequency divided by 2. And you must keep in mind, as much higher the percentage, the wider the bandwidth you will get. In this way, you can do this in all tabulated form. This is s22 block. This is almost similar to s11 block. There is a slight difference. In my coming tutorial, I will do some changes in tri-band and quad-band filter, and I will check the results, and I will compare S1 and S21 parameter, and also I will tell you how to shape the band and how we can create in dual mode bandpass filter. How we can make it a tri-band bandpass filter. How we can make another passband by splitting this passband filter, and I will demonstrate the terminologies used in this project in my HFSS tutorial. You must go in my channel playlist to find HFSS tutorial series, where you can search these tutorials and many more other from basic to higher level. After that, you will be able to implement any research paper on HFSS.